We do not truly know the Milky Way galaxy, even though we live inside it. And no, I'm not referring to niche details like stellar formation or how galaxies evolve. Even the fundamentals remain unclear to us. How many stars are there? What is its actual shape? Does our galaxy have 2 spiral arms or 4? It might sound like a simple thing to figure out, but we still don't have a definitive answer. Estimates of the star count vary widely, from 100 billion to as high as 400 billion. And over the past 20 years, scientists have gone back and forth between 2 or 4 arms. Currently, the consensus leans toward 4. It makes sense, in a way. Looking at something from the inside is naturally harder. It's easier to stare out your window at the house across the street than to try and see your own house from the inside. But here's a fun question for you. How many galaxies are inside the Milky Way? According to ESA's Gaia space telescope, which just wrapped up its 10-year mission, the answer isn't just one. Gaia has mapped the stars of the Milky Way with over 3 trillion observations. Now, as it completes its final review of our galaxy, something strange is emerging. About 30,000 stars are moving in unusual ways. They're going the wrong direction. These stars didn't originate here. They came from outside the Milky Way. As I mentioned, observing our own galaxy is surprisingly difficult. All the stars, dust clouds, and gas in the way make it tough to get a clear picture. This problem gets even worse as we look toward the center of the galaxy, where matter is most densely packed. That dense region is known as the zone of avoidance. Visible light struggles to pass through it, forcing astronomers to rely on other tools, like X-rays, to see what lies beyond. Back to our earlier analogy, it's like sitting in your bedroom and trying to figure out the layout of the entire house while walls block every line of sight. On top of that, it's extremely hard to measure how far a star is from Earth. To build a proper 3D map of the Milky Way, we need to know, is a star nearby and small? Or is it far away and massive, just appearing faint because of its distance? Some stars help us out, like Cepheid variables, which have a predictable brightness that lets scientists estimate their distance. But many stars don't make it that easy. So how do we know how far away those more unpredictable stars are? The answer is parallax. That's the principle Gaia has been using for the last 10 years. Parallax means objects appear to shift position depending on your viewpoint. You can try it now by holding a finger in front of your face. Close one eye, then switch to the other. Your finger seems to move compared to the background, right? The closer the object, the more noticeable the shift. This is how Gaia determines distances, using precise, repeated measurements over time. While the finger trick shows the idea clearly, it only works over short distances. When it comes to measuring a star's distance, we need a much wider baseline than the space between our eyes. That's where Earth's orbit comes in. Every 6 months, Earth moves to the opposite side of the Sun. This creates a much larger separation, about 300 million kilometers. Using this baseline, Gaia captures tiny parallax shifts in the stars' positions. Imagine a time-lapse of the night sky, taken over several years. In these animations, stars appear to move in looping patterns. But that motion isn't from the stars themselves, it's us. Our movement around the Sun creates that apparent wobble. By tracking those loops, Gaia can calculate how far away stars are. And Gaia doesn't rely on just 2 measurements per year. It's been observing stars repeatedly over an entire decade, making its results far more accurate than anything before it. But there's an even bigger baseline to work with: proper motion. Not only does Earth move, but so does our entire solar system, along with every star in the Milky Way. These motions give us an even larger framework for measuring distance. The same parallax principles apply. Stars with large proper motion tend to be closer to us, while those that drift slowly across the sky are typically farther away. Using this method, Gaia has built an incredibly detailed 3D map of our galaxy. But Gaia didn't just map star positions and movements. Its mission went far beyond that. It also studied each star's luminosity, temperature, mass, and chemical makeup. This helped scientists understand not just where stars are, but what they are made of, and how they live and die. Gaia carries two powerful telescopes. Each channels light from different directions into a billion-pixel camera, the most precise ever flown in space. Its radial velocity spectrometer measures Doppler shifts, revealing how fast stars are moving toward or away from us. It also has photometric instruments that study starlight to determine their composition and temperature. So even though Gaia's map includes only 2 billion stars, a fraction of the Milky Way's total, it's still the most detailed map of our galaxy ever created. And this data spans time. Gaia has been collecting observations since its launch in 2013. That decade-long window allows scientists to not just map our galaxy, but to watch how it has evolved and moved across time. Thanks to these long-term observations, Gaia has revealed that our galaxy has a history of consuming others. And now, with enough data, scientists can rewind the movement of stars, creating a model of how the Milky Way grew by eating smaller galaxies. And with that, they were able to reverse engineer the history of our Milky Way's structure and its violent past. Photographing our galaxy from the outside is impossible. No spacecraft has traveled far enough to capture such an image. But thanks to Gaia, we now have a stunning digital model, one with incredible accuracy based on real motion and data. One strange detail immediately stood out. The Milky Way's edges aren't smooth. They wobble and ripple, suggesting the galaxy collided with something. Digging into the second data release, researchers in the Netherlands focused on a set of 7 million stars and found something odd. About 30,000 stars were moving in the opposite direction from the rest of the stars in the galaxy. That motion alone was suspicious, but there was more. These stars also had different brightness and color signatures. All signs pointed to one explanation. These stars came from another galaxy. A small dwarf galaxy had collided with the Milky Way between 8 and 11 billion years ago. Scientists named this ancient intruder Gaia-Enceladus, or sometimes the Gaia-Enceladus sausage. Its stars, shown in red in some visualizations, once formed a relatively compact group. But over time, they were pulled apart and spread across the galaxy. This merger likely helped shape features we see today, including the Milky Way's central bar, something only 2/3 of spiral galaxies possess. Gaia-Enceladus wasn't the Milky Way's only late-night snack. Another dwarf galaxy, known as Arjuna, Sequoia, or Itoi, was also discovered to have merged with us. Some researchers believe it may have even traveled alongside Gaia-Enceladus, but it didn't stop there. Later studies revealed signs of more ancient collisions. In fact, evidence suggests that the Milky Way may have swallowed up as many as 6 galaxies. One of the most fascinating ongoing events involves the Sagittarius dwarf galaxy. This small galaxy has collided with the Milky Way 3 separate times over the past 4 to 5 billion years, and it's not finished yet. Sagittarius is still interacting with the Milky Way today, gradually being pulled apart by our galaxy's gravity. Its stars slowly absorbed and scattered into the galactic disk. Some scientists believe one of these past collisions may have triggered the birth of our own sun. Eventually, Sagittarius itself will be fully consumed, becoming the 7th galaxy devoured by the Milky Way. Each of these mergers left behind distinct star populations, moving in strange ways or showing chemical fingerprints. That revealed their alien origins, and Gaia's data is what allows us to spot them. These discoveries are just a glimpse of what Gaia has made possible, but sadly its mission has come to an end. Gaia maintained its position at the second Lagrange point, using cold gas propellant, about 12 grams per day. Eventually, that fuel ran out. On January 15th, Gaia took its final observation. It will now go through a few final calibrations. before fully powering down on March 27, 2025. But the story isn't over. Gaia still has more to give. 2 major data releases are yet to come, and they hold some of the mission's most valuable findings. The first is Data Release 4, arriving in 2026. It will contain a massive 500 terabytes of information, covering just the first 5.5 years of Gaia's work, but in much greater detail than anything released before. This release could highlight stars with subtle wobbles, possibly pointing to the presence of exoplanets. It will also include the most extensive catalogue of binary star systems ever created. Even more is coming with Data Release 5. Expected near the end of the decade, this release will include the full 10.5 years of Gaia's data, at the highest precision imaginable. Together, these releases will offer a cosmic treasure trove, giving astronomers tools to study the Milky Way in ways never before possible. What else might we discover hidden in that data? The power of Gaia's data doesn't end with past galaxy collisions. Because it tracks star positions and motion over time, scientists can use it to project millions of years into the future. We can now model how stars around us will shift and move across the galaxy. In some of these models, nearby stars first appear to scatter, then later regroup in certain areas. This effect is believed to be caused by density waves, which are responsible for creating spiral arms in galaxies like ours. Understanding this movement helps explain why our Milky Way looks the way it does. But Gaia's reach extends even closer to home. It also studied thousands of objects within our solar system. The positions and trajectories of over 150,000 asteroids were mapped with stunning precision. And because Gaia could track how they moved over time, it found that 352 of them likely have moons. These tiny orbital wobbles gave away their presence. This discovery nearly doubled the known number of binary asteroid systems in our solar system, a massive leap forward in planetary science. Gaia has often been called a treasure trove, and it's easy to see why. The scale of information it gathered is unlike anything that came before. And this is only scratching the surface. Gaia has helped locate black holes, quasars, and more. It's hard to overstate just how much this single mission has reshaped our understanding of the cosmos. One of Gaia's most impressive contributions is the creation of the largest ever 3D map of quasars. It identified 1.3 million of them across the wider universe, some from when the cosmos was just 1.5 billion years old. These distant beacons have helped refine our understanding of how the universe evolved on the largest scales. And closer to home, Gaia made a surprising find. Within our own Milky Way, it discovered a previously unknown black hole, 33 times the mass of the Sun, located just 2,000 light-years from Earth. Until now, most black holes in our galaxy were far smaller. Typically, stellar black holes we've found are only about 10 times the mass of the Sun, so this one stands out as truly massive, a unique find enabled by Gaia's unmatched precision. All of this leads to an important question. What comes next? The European Space Agency is already considering a follow-up mission called Gaia-NIR. This telescope would operate much like Gaia, but it would see much deeper into the infrared. That means it could peer through the gas and dust. That blocked some of Gaia's vision. But don't expect it anytime soon. If approved, GaiaNIR wouldn't launch until around 2045. That delay is intentional, to allow the stars time to shift for more parallax effects. When it arrives, Data Release 5 will be the crown jewel of Gaia's mission. It's expected by the end of the decade, and will include all 10.5 years of data Gaia collected, processed to the highest level of detail ever achieved. This release will provide a complete snapshot of the Milky Way's stars, movements, and structure. And it will be so rich in raw data that scientists may uncover discoveries for decades to come. Just imagine what secrets might be hiding in 10 years of deep space precision. New exoplanets, unknown star systems, even more evidence of galactic mergers. So yes, Gaia's mission is ending, but its legacy is just beginning. It has given us the best opportunity we've ever had to truly understand the galaxy we call home. Our Milky Way is vast, ancient, and complex. But thanks to Gaia, it's no longer just a blur of starlight. It's a living, moving map, one we can explore in 3 dimensions, across space and time. And there's still more to learn. Gaia has shown us that even from the inside, we can discover the shape, history, and secrets of our galaxy. All we need is patience, precision, and a clear view of the stars.